Hi, welcome back to this video in engineering dynamics. So in this video we're gonna do some sample problem for the rotation at a fixed point. So in this problem is actually taken from the textbook of Hibbeler. So the problem is F16-1. The problem states that when the gear rotates 20 revolutions, it achieves an angular velocity of 30 radians per second. Starting from rest, and the problem says determine its constant angular acceleration and the time required. Okay, so this is the figure. We have a gear here, and then it's rotating. Um, it rotates from rest. So I mean, it starts from rest, and then it achieves a velocity of 30 radians per second after 20 revolutions. Then we are asked to determine the acceleration and the time required to achieve the angular velocity from 0 to 30 radians per second. Right, so for the solution, then we'll sketch a figure here. Okay, so the figure is there's some point one here. So let's say this is point one, and then after let's say after 20 revolutions, let's just put it here. All right, so this is point two. So take note, this is not really an exact or accurate representation, but at least we'll be able to follow the what's required or what's missing if we'll draw it this way. So we have point one here, and then after some 20 revolutions, let's say this is point two. So here the problem says that it starts from rest, and therefore the initial angular acceleration here is 0. And then since it's the reference point, then our theta here would be, let's say theta 1 would also be 0. So after some 20 revolutions, so let's say we have 20 revolutions here. So our velocity here is 30 radians per seconds, and also I think this revolution is also a position, so we can convert this 20 revolutions into radians. So theta sub 2. Okay, so solving. Alright, so solving for theta sub 2. So our theta is, what's given is 20 revolutions. So times the conversion between the regions and the revolutions, which is 1 revolution is equal to 2 pi radians. If you try to compute that, then 20 times 2 pi, alright, 40 pi or 125.6. Right, so 125.6 6 regions, or you can use the 20 pi if you want. Right, so recall that this is an angular acceleration problem. Is constant acceleration. Constant acceleration. Because it says determine its constant angular acceleration in the time required. So therefore, the working equations would be we have the distance and also the velocity. I mean the angular distance and then the angular velocity. So we can use the equation, this one, to theta. I think this should be delta. Right, delta theta is equal to, what is that? Delta v squared or omega squared. Right, so since we have the values of these and as well as the angular velocity, then we can solve for the alpha. So alpha is equal to, what is this? It's just simply minus squared all over 2 times delta theta. Right, so the change in theta is just theta 1, theta 2 minus theta 1. So here the angular velocity is 30 radians. So 30 squared minus 0 because it's from rest, and then this one 2 times the theta 2 is equal to 125.6. So minus the position here. So since it's the reference point, then it's just 0. Right, so 125.6 times 2, and then 30 squared divided by answer. So what we get, 3.58. So 3.58 radians per second squared. Alright, so the next thing is we are asked to solve for the time. As I said, the time required to achieve the 30 radians per second angular velocity. So solving for the time. So the equation that we'll be needing is we have this, or we'll just use the average one, it's okay. Right, so since we have this value, the angular acceleration, plus we also have this value, so we can solve for this, the time. So take note, it's a delta t, but since at this point, point 1, t1 is equal to 0 since it's the starting point. So t sub 2 is here, and that's what we are trying to find. So delta t is equal to change in the velocity divided by the acceleration. So t sub 2 minus t sub 1. T sub 1 is just 0, so therefore t sub 2 is equal to so 30 radians per second, okay, minus 0 divided by our acceleration, which is 3.58 radians per second squared. So t sub 2 is equal to, so 30, we have 8.37, right? So 8.37 seconds. Alright, so let's have a recap on the process. So the problem is that this gear is rotating at some from rest, and then after 20 revolutions it obtains an angular velocity of 30 radians per second. So we are asked to find the constant acceleration and the time to, or the time required to achieve this angular velocity. So we draw this illustration. So again, it's not a very precise illustration, but at least we can. For me, I can look at what's missing. Like for example, the point one and then the point two. What's I mean the variables here. What's missing or what's given. So at least I can follow up. So that's why I do it this way. So first, since we are given 20 revolutions, it's actually the position here, because 20 revolutions from rest, so meaning this is the the starting point. So the 20 revolution is just this one. So we convert the revolutions into radians and we get the answer 125.6. And then since the problem is a constant acceleration, then the equations for constant acceleration we can apply for this problem. So one of the equations is this one. The we have in this equation we have the angular velocity and then the distance and then this angular acceleration. So this one is given both point 2 and point 1. This one is also given point 2 and point 1. So we can solve for this angular acceleration. And then after that we are asked to solve for the time. So we use this equation. So the change in the angular velocity divided by the time is the acceleration. So since this one is given, this two is given, so we can solve for the time, and then the answer is 8.37 seconds. Alright, so in the next video we'll be doing another sample problem for the rotations. See you in the next video.